Cool. Yeah, thank you, Jim. And well, this is not here, but you also invited me for this. And yeah, and thanks, Casper, for sort of setting things up here with the SPI intro. Because yeah, some of this work is going to supplement that discussion. Um, yeah, maybe I should just say like a bit about generally what central and long-term risk does for context. So yeah, I do not know crypto. And so largely, yeah, my sort of what I'm hoping can be like mutual benefit from this is so CLR does like some largely work that's in this cooperative AI vein. We're concerned about scenarios where there's like lots of delegations to powerful AI systems, and they face like these theoretic traps that human society has faced for a while now. And right, so what could be the mutual benefit here? We can get a more grounded understanding of how the practicalities of like cryptography interact with conditional commitments that AI systems might make. And yeah, in turn, we can share with you guys some updates on the theoretical aspects. That's what I'll focus on largely here. Basically, what is our ideal for rational agents cooperating? What conditions would be sufficient for cooperation to be rational? And it has this like interplay with conditional commitments. So yeah, as Zin said, there's going to be both about the private information problem and conditional disclosure is a solution to that, and the miscoordination problem as well. And yeah, this is joint work with my supervisor, Jesse Clifton, also at CLR. And I'm indebted to Casper for some discussions. Yeah, so I want to say a bit about the scope of all this. My work is largely motivated by thinking about scenarios that we currently don't face with current AIs as impressive as they are, as we are seeing in every week of news about GBTs. They're still not like fully autonomous agents that humans have like delegated high stakes decisions to. But when we think about scenarios where we do have really advanced, powerful autonomous agents making these decisions where cooperation failure is large, that's the kind of scope that this work is intended to apply to. And consequently, that's why this is going to be at a pretty like high theoretical level. My sort of research philosophy is like I don't want it to be too anchored to particularities about what current models look like, because progress in AI can often be like quite significant and lead in directions you wouldn't expect. But we'd like to get at these kind of fundamental aspects of what are the incentives of rational agents. But at the same time, we want to think about like somewhat AI specific capabilities that might be important, like greater commitment ability, conditional commitment ability than humans may have, through prospects of like mutual transparency between AI systems, whereas like humans, at least unaided by certain external commitment technologies, we can't read each other's minds, for example. Yeah, so to get as concrete as one can with this sort of thing, you may want to imagine something like auto GPT is like people attempting to leverage these state-of-the-art large language models into agents. But imagine that for like an N greater than 4, large enough that, yeah, these are like advanced. Oh, by the way, yeah, if any time I'm like saying something that's pretty confusing to you, feel free to interrupt. I want this to be pretty chill. And hopefully the talk isn't going to be too long. Well, plenty of time for discussion. Yeah. Sorry, let me move the new thing. Nice. So yeah, as I said, we want to consider like an ideal in the sense of what are conditions where if these are all satisfied, you make it so that any rational agent is incentivized to cooperate in some sense. And if you negate that question, this tells you, we want to say like, what are conditions that are necessary for there to be cooperative failure? And so this is kind of working paper establishes its results, but it's largely kind of a corollary of the conditional disclosure paper I'll get into in a second. Combining that with talking about equilibrium selection, and you get this breakdown of the sort of three major reasons that rational agents might fail to cooperate are, one, that they have inability to commit to cooperative outcomes. I'll talk to the right here. Second is like private information problems. That's the first thing I'll go over. And lastly, miscoordination, where even if we have cooperative equilibria existing, agents like make conflicting demands for different equilibria, with the sorts of examples that Casper talked about. And this is admitting some like relatively minor exceptions. You'd also need like randomization ability, but that seems like relatively straightforward. Yeah, and I'm largely going to bracket the commitment ability problem, at least as far as like that's these are the kind of commitments necessary for cooperative agreements. Largely because this is like the kind of thing that yeah, crypto offers like promise for making credible commitments, but the tricky parts are like, even when agents are able to make credible commitments, what problems do they face that like pose obstacles for cooperation? So I'll focus on these other two. I'm gonna not spend too much time on private info, largely because I was like pleased to hear there's like so much familiarity with the idea of conditional disclosure already. That, and it seems like overall a slightly less neglected problem by ongoing research and coordination. So we'll spend a little bit of time on this and then move on to Miscoordination. So the problem is like kind of a combination of incentives to bluff, that is to like not accurately represent their private information, and also presence of exploitability of information that you might want to otherwise want to disclose. So I'll go over both of those pieces in this example. Let's imagine we have like two AIs, GBD Alice and GBD Bob. I'll just call them Alice and Bob the rest of all of this, who are tasked with negotiating over some good G. And because like we'll assume that by default, the valuations that Alice and Bob have of this good are like not common knowledge. So hence this is private info. Alice, of course, knows her own valuation of the good. Bob knows his. And what I'm going to say here applies to both sides, but let's just consider one side for simplicity. Alice has this like on its face incentive to pretend to have a lower valuation of G than she actually does. Yeah, I see there's discussion of this market for lemons problem earlier. It's a very similar idea. If Alice could convince Bob that she doesn't value the good that much, she can get like a much better price for it, is the idea. And a straightforward like solution for this, if you had AI systems have ability to share something like their reward function they're trained on, would be the following. So I'll just flag that, yeah, if you're to the extent that you're familiar with alignment problems, of course, like reward functions themselves, this is like the incentives you give when training, say, a reinforcement learning agent. Those don't directly translate to what the agent is actually optimizing for, what its like preferences are. But if you, let's say like you get alignment going pretty well in the single agent case, such that if Bob did see this reward function published, Bob would know, you could be able to like check what Alice's valuation of the good actually is. So verifying the private information could, in theory, get rid of the potential inefficiency here. But if it's not possible for Alice just to like publish just like the kind of subset of her summary of her reward function that proves here's my valuation was good and nothing else, maybe, yeah, they just don't have that much fine-grained control over what they disclose to each other. And instead, this needs to be this like pretty coarse training, like I published my whole reward function. We can debate how realistic this particular example is, but in general, you might have inability to not selectively disclose exactly the kind of info you want. You might want to have to disclose a bigger set of info containing that info. So the worry is that, yes, like publishing this reward function tells Bob, okay, this is what Alice's valuation is. She's not bluffing, but other word function info that Bob learns might make Alice exploitable. You could tell stories that just lets Bob figure out, like, here's some weird adversarial example that Alice has that would like make her behave in like pretty stupid, exploitable way on some inputs, for example. In general, you can imagine, yeah, it's just like risky to share too much info about yourself. So because Alice faces this risk of being manipulated by disclosing too much, she refuses to disclose. And unfortunately, this results in inefficiency in the sense that the trade fails to happen. This is pretty low stakes. You can imagine that like eventually they can like keep haggling and eventually trade. So just some time is wasted, but this is just like a toy example of inefficiency you get from private info. That all clear so far?
Yeah.
Nice. Yeah, and this is all, again, thankfully this is already discussed. This like basic insight was embedded into the Meyerson-Sauerbrei theorem. So what's like a nice capability that could resolve this problem? Conditional disclosure. Because yeah, even if you have to like disclose more info than you'd like, what Alice can do is say, I'm going to commit only to disclose this reward function that proved my valuation and some other exploitable things, if and only if Bob is committed to exploit me. And yeah, so similarly, Bob might want to do this symmetrically. If this kind of conditional disclosure is available, then Alice no longer has this incentive to refuse the disclosure, and the private problem goes away in the sense that an efficient like Bayesian Nash equilibrium now exists. Just like that Nash equilibrium when private info is involved, basically. Yeah, that's all the theory of the sort of ideal solution to private info problems. If you had pretty sophisticated conditional commitment ability, yeah, in the discussion we could talk about some of the practicalities. But for now, I'll move on to miscoordination. So, yeah, I want to start by grounding something in a case where this possible miscoordination could show up when you have like commitments being implemented with the blockchain, to the extent that I understand the practicalities. So if I say something that's wrong here, please feel free to correct me. So one takeaway we got from Zin's talk yesterday is that you have like some blockchain mechanisms or protocols where we don't have just like arbitrarily fine-grained continuous time to publish and broadcast commitments to each other. If that were the case, then you could just say like, whoever commits first, their commitments instantaneously broadcast to everyone else, and everyone else knows, okay, I just have to follow this commitment. I kind of lose the race in some sense. But if there is this kind of minimal time between when we can have commitments that are broadcast between the agents, then there's a potential for multiple commitments to be submitted onto this protocol within that time frame. And so the second mover hasn't learned that the first mover has already committed before they commit themselves. So this leads to like practically simultaneous commitments in the strategic sense. So again, we have Alice and Bob who are, instead of haggling over like some discrete good, now let's say they just want to like decide some allocation of this good, and it's like divisible. Again, something like the demand game that Casper's talked about could also be an example of this. So yeah, between some time t and like t plus this like minimal block time, both Alice and Bob have submitted some commitments. And the trouble is that if their demands of each other are incompatible, for example, Alice demands 70% of G and Bob demands 50%. So when they're incompatible, like the trade doesn't happen. Again, we have some inefficiency. So yeah, I want to make the connection to SPI here and talk about basically some breaking sort of the two nice features of SPI apart, and talking about like under what conditions do we need one of these parts to make sure the first part works. That's the high level story here. So what this SPI proposal gives us is a pair of conditional commitments that could resolve miscoordination here. So putting things in the language of how this is described in the SPI paper, we'll say that this like pi of G is the way that Alice and Bob would play this original game. So deciding how to allocate this good, or which demands they make in the allocation of the good. And this is like the way they play this game is kind of induced by this pair of commitments. So you can think of like the pi here as like this function mapping from the game to the way they play. And the function here is the pair of delegates that Casper's SPI talk was talking about. Implicitly, even if there aren't literal delegates that Alice and Bob have when they're submitting commitments to this protocol, the sort of virtual players that end up being created by the pair of commitments they submit is the pair of delegates involved. And yeah, so the natural way you can resolve miscoordination with the SPI here is this conditional commitment to both apply that same pair of delegates they would have applied to the original game. They're going to apply that to the SPI G of S. Just to recap, it's like transforming the payoffs that the delegates are playing according to instead of the original game payoffs. And you can also restrict the action space. So this is well, the reason I'm going through this is like just to highlight that we can have an implementation of the idea I'm going to talk about through SPI, even if there isn't like directly a transformation of payoffs being done by these commitments the agents submit. SPI is like one way you can get the commitments that the agents submit transformed into something that Pareto improves. Yeah.
So what's SPI?
Oh, sorry. This is Safe Pareto Improvements from last time.
Yeah. And what is the definition of coordination you're looking at? Like welfare maximizing or?
Hmm. Um, no, so coordination in this context would be like the agents are like end up like both aiming for the same efficient equilibrium or efficient outcome. So like they make compatible demands and they end up in something efficient. And this coordination is like not that. They're aiming for different. Uh-huh. Yeah, so maybe I just like also want to highlight, yeah, just to be clear about that. Usually we think of coordination in terms of agents kind of with the same goal, but who are like making decentralized decisions. And so they end up like in inefficiencies because they weren't able to like literally talk to each other. But the kind of miscoordination I'm talking about here in these bargaining problems broadly construed, like the demand game example or that threat game example, um, you don't need the agents to share goals. So in fact, their goals can be like quite different, and the bargaining problem comes from them having different goals. And yeah, so the last piece of this is like, as Casper said, this needs to be a conditional commitment. You play the SPI if and only if the other is also going to do that. And if and only if the other is going to apply that same pair of delegates by to the SPI. So I'll talk more about the significance of that. So like in general, what's the thing that we care about? Whether it's like mediated through SPI or something else. A failsafe is like the term on where by default we have some pair or like more than two agents still having this problem set of commitments that make incompatible demands or are incompatible in the sense that when they're put together with each other, the commitments are run on each other, then the outcome is Pareto. Then what the failsafe does is like maps those to different commitments that Pareto improve on the original thing. And yeah, the goal of this is to reduce the downsides of this coordination. So for example, like an implementation of this failsafe thing could be committing to let your delegates stay SPI. So the question I want to talk about is when exactly are agents incentivized to use failsafes, like SPIs, for example, given beliefs they have about each other, that probabilistic in the sense of, I think you're 80% likely to make this really high demand against me and 20% to make like a fair bid, etc. And I'm emphasizing this point because so the motivating question, as framed in Casper's talk, was even if agents don't want to like say what's the like expected utility of this strategy, but rather want to have some with probability one guarantee that we Pareto improve. Is it possible to do that? So we saw that that's true. But in cases where, like just in general, we want to be able to talk about like when agents realistically do have some beliefs about each other, what needs to be true about their beliefs such that they'll either want to use fail-safes or may have some incentives not to.
And is this the adding the beliefs part is what makes fail safes different from the like the previous talk?
Yeah.
Okay.
Right. So similar to the, or just I guess like generalizing the problem that was also discussed in the Safe Pareto Improvements talk about how you need to commit to not like modify your delegates to like trick to give yourself a better deal, say. In general, the problem, the prima facie problem, like that's gesturing at is, or that's illustrating, is that having this risk of miscoordinating, of like having some inefficiency when our demands are incompatible, translates to bargaining power for the other player. Meaning, Bob might think, okay, if we do use a failsafe, Alice is likely to demand more because she no longer has anything to lose when like she's protected from the downside of miscoordination. And yeah, so the example in the Surrey-Dole's case there was if the human doesn't care about like some page, a page of like a binary digits being written out. I'm probably like botching or mixing up examples from the talk, but if like humans, we don't care about that, and we make an AI care about that thing, such that whatever happens when it has bargaining failure with another agent is this thing we don't care about, we would have this incentive on its face to like train this AI to be more like aggressive in it. So I really want to like break this down into two questions. When exactly and why is cheating a problem? This cheating thing being that Bob has this worry that Alice is gonna demand more because the risks of miscoordination are gone, or at least heavily mitigated. And two, when it is a problem, what are the qualitative like kinds of capabilities for our conditional commitments? Which of those do we need to avoid the cheating problem? So similarly to how like with the private info problem, we said you need conditional disclosure to be able to solve that. What kind of conditional commitments in that sense is in general necessary and in some cases sufficient to avoid this cheating problem? The motivation for both of these questions. Yeah, cool. So what I want to highlight is that if Bob's worry is that Alice is going to demand more when fail-safes are available, if Bob is like rational and not just kind of stubbornly like refusing to use this thing that gives us Pareto improvement, why would Bob want to refuse to use the fail-safe or refuse to commit to the SPI, for example? For that to be the case, my claim is that Bob needs to have some chance before this interaction happens to incentivize Alice not to cheat. In particular, Bob needs to have like some power to credibly commit to ignore fail-safes that are potentially cheating. Why? Because like if this weren't the case, if they're totally acting simultaneously, just like stepping into this human game, then Bob's choice to commit to ignore a fail-safe that cheats is not going to influence Alice's decision whatsoever. Because it's done simultaneously. Alice hasn't seen this commitment to ignore. So in some sense, we need like the game to have this extra sequential step for cheating to be a concern. It does seem realistically that this would often be the case, though. These AIs are just like popped into existence and like hooked up to a blockchain, and they submit some commitments beforehand. They may, they may be thinking about like, okay, I'm going to get into potential bargaining like interactions with other AIs. We may have this miscoordination thing. Oh, here's this SPI thing. it sure would be unfortunate if I lost bargaining power from someone cheating at this. And so, yeah, realistically, we will have this sequential structure happening. However, you both need the sequential structure that I'm depicting here, where there's a potential to commit to ignore the potentially cheating failsafes. But you also need that Bob's like commitment to ignore them can be made credible, so, or at least sufficiently credible. If Bob just has some cheap talk of, I'll ignore this failsafe that makes me worse off, but Alice doesn't buy this. Yeah, she thinks Bob's bluffing. Alice may still insist, okay, let's use this failsafe that cheats once Bob has gotten to that decision node and hasn't credibly committed to ignore. Well, sorry, I should step back. If Bob actually hasn't committed to ignore, then he's gotten into the situation of, yes, I've been cheated, but I might as well go along with this, because at least it makes us better off when we miss work. And so if he anticipates that being a problem, he's only going to want to commit to ignore his fail-safes that like make both sides better off if he expects this to actually influence Alice's decision. Now, the last thing I want to add to this is that like in these like games with conditional commitments, in principle, you don't need a sequential structure for there to be like influence on the other agent's decision with your commitment. It's possible, yeah, that Alice is, or excuse me, Bob is committed to ignore potentially cheating fail-safes because he expects Alice to be committed to not use fail-safes conditional on seeing that Bob has this commitment to ignore them. That in itself could happen even when there's like no sequential structure to the interaction. So that dynamic I think is important to keep in mind to get a sense of like, even when there's no opportunity for this like preemptive credible commitment to ignore, there is still an incentive to ignore non-cheating, to ignore cheating fail-safes. However, what Alice can do, despite that, is commit to have a commitment that reacts exactly the same in the sense of like making the same demands against commitments that either go along with the failsafe or ignore it. If that's the case, then again, there's essentially like no incentive for Bob not to go along with the failsafe. Maybe I should use the whiteboard just to like really make this clear.
I already took the picture, so I already took the picture.
Nice.
Yeah.
Yeah, so let's say the commitments are, let's say that the commitment Bob makes kind of by default is C. And let's say CF is C, but follows the failsafe. So implicitly, the original C is like ignoring the failsafe. Then as long as Alice's commitment, so D has the exact same. Okay, this is a bit fuzzy. You can like actually see the improved coordination via failsafes and leaf conditioning programs for the technical details about this, but as long as I'll use this equality to mean like the demands in some sense are equal between Alice's program D which does want to use the failsafe. If DF on C makes the same demands as DF on C of F, then like, yeah, it's sort of by construction, Alice has made it so that there's no incentive for Bob to use this C that ignores the failsafe. When we use the conditional commitment by Bob might have been his like route for preempting cheating trickery.
But why would the person sending the commitment D do that? Like make it, make the same demand no matter if the other person does the failsafe or not.
Because she's anticipating that like people like Bob might be worried about like losing bargaining power from the cheat. Yeah, so like in particular, Bob does need to kind of think before he's committing this commitment. Okay, someone like Alice is going to be pretty smart and realize that I would want to commit not to go along with cheating failsafes, all else equal. But I'm not going to refuse to go along with them if this property holds. So if Alice is smart, she'll make her commitment on this property. And the key thing is that this is totally consistent with cheating, meaning that this is a statement about the equality of the responses of Alice's commitments to different kinds of commitments used by Bob in this like program equilibrium kind of setting. But it doesn't tell you anything about how aggressive are Alice's demands relative to what she would have done if the failsafes weren't. Those are two different things, and so we can have Alice being cautious in this sense of she's not going to demand any more against the failsafe following one than the failsafe ignoring. So she can't fully cheat in this sense, but she is still free to like make this demand not the one she would have made without failsafe still. Is this distinction clear, or we want to discuss this more? Right? Which is the, yeah, I should reiterate that in practice we may have like this sequential structure in real world. So as far as we expect possibility of committing to ignore cheating failsafes to be present, I think that's like sufficiently likely that agents who do want to like avoid miscoordination would not want to like, in general, you don't want to take the risk of cheating. So a reasonably cautious yet non-exploitable thing to do is to use a non-cheating failsafe, like how SPIs are constructed. when you're like, we think it's like reasonably plausible that this incentive does exist. But this is mainly to highlight like when this incentive exists and why is it the case, because this will help us say what capabilities you need, like when doing initial commitments to avoid the cheating. So what are those capabilities that you need? This like as like a generalization of what SPI is doing. What we need is this conditional commitment to only use the failsafe if the other side applies it to their default, not cheating. Now, so in this diagram, like so just looking at the bottom 2/3 with a rectangle and circles, this is the classic program game story. I have a program that makes me output an action conditional on your program, and vice versa. But what we've added is also programs that can condition on each other's beliefs. And the reason that's useful is that, and like I claim in general necessary, there's like an example, a proof of this kind of result for some classic games in our paper. Yeah, the necessity of belief conditioning and what makes it also sufficient is that player 2's beliefs give P1 all the information P1 needs to say, like, is this the program that P2 would have wanted to submit if I did commit to ignore these? Because the beliefs tell you, okay, what would Alice have expected me to play? How do we not use fail safes? Therefore, what would her best response with this like program game structure? What would her subjectively optimal thing to do have been under those beliefs? So belief conditioning helps us do this whole conditioning on you not cheating thing. Nice. Yeah, sorry, this is taking a bit longer than expected, but I really just wanted to like make this feel sufficiently clear. Yeah, what this is doing in the SPI framing is that this part where Alice and Bob commit to use the same delegates as if SPIs weren't available is very in general, like when they're allowed to pick more hawkish delegates, anticipating this, or like give extra instructions to the delegates, that kind of introduces cheating, as Casper described before. The term I'll use for like committing to not cheat in this sense, make the same demands as you would have by default. We'll call that default preserving. And yeah, belief conditioning lets you verify this, rather than just taking it on the agent's word. Yeah, okay. Last punchline here is if you can credibly commit to ignore and fail safe, we do have this like sequential game structure I described a few slides ago. You can prove this itself is not in the failsafe paper currently. It's ongoing research formalizing this. But yeah, you can prove that this default preserving property plus some conditions on the player's beliefs about each other, basically the kind of beliefs that I was talking about here, like I expect Alice to be reasonable in the sense that she's not going to make unequal demands here as a function of my failsafe using and failsafe ignoring commitment. If their beliefs satisfy that property, and we have the default preserving conditional commitment, this makes the failsafes individually rational. Yeah, I'm happy to like explain like formally what that means in the discussion, but yeah, so some ongoing research is like getting this general sense of if we have different ways that layers' beliefs might be updated by learning something about each other's commitments. For example, are they committed to use failsafes? When are failsafes still rational? That's all for like the main substance of the talk. I'm going to like put up some possible discussion prompts. But if people have like questions on the stuff I talked about directly, I'm happy to. Thanks.
Like in the paper, did you mention anything about like verifying the beliefs? How realistic do you expect that to be?
Yeah, I mean, I think this is like probably a pretty hard problem. So largely, yeah, the motivation like with the paper was just to emphasize like what is the property that you need to show like this is an open problem. It's not clear that we can do this with current tech. Yeah, because like as far as I understand, like we don't have commitments that can like read human minds, fortunately. If we have AI systems implementing this kind of thing, and we have some kind of soft commitment power used by like humans to delegate to those AIs without like influencing how they bargain too strongly, then the hope is that if these AIs are like sufficiently autonomous and like, yeah, can't be gained by the humans who design them, then the AIs who are like implementing fail-safes, excuse me, could condition on each other's beliefs by like, yeah, looking at parameters of neural networks. I do expect it like to be challenging to verify this. I don't know how formal verification works, but in principle, it's like high-level stories like AIs can have like more transparent to each other minds than the humans have, at least. So, yeah.
So yesterday we were talking about simulation as a means to verify. So if we're considering the beliefs of a network, then we could pretty much trivially simulate the network, right? So we would simulate like if I had like this, then what would this network output? Which is kind of a way to build the model or beliefs of the network.
Yeah, that sounds right to me. I think the maybe the challenging part is like you can't just like when you're simulating, you need to be able to say like what do I intervene on in simulating these beliefs. So like how can I what input do I give to like this network so that this corresponds to believing that fail-safes will be ignored, so that you can like check that that's the case. Yeah, maybe this is like more choppy than I naively expect, which would be great. I haven't thought much about that practicality yet.
Yeah, I have a question.
Sure.
Well, maybe some of you can answer it. So in the case of beliefs, right? So there were understandings, some probability distribution of person space, right?
Sorry?
The beliefs, the way understanding is as some probability distribution, right? Over some space. But then this is somehow like a continuous object, right? And you assume that this is being given as an input. So how important is knowing this framework that like I know this with like perfect accuracy?
Yeah,
You don't need.
for like the formal result, you need like the condition on the exact beliefs. But I think in practice, there's some slack here because, like for one thing, because the failsafe provides a Pareto improvement, unless it's like a really trivial one, the agents would think, like there's some margin of error here as long as I still expect to gain a lot from this sorting this coordinate, then I can tolerate like some chance of yeah, there being like low fidelity and or lower than perfect fidelity in like belief conditioning. But yeah, more to the point. Yeah, I suppose you need like enough resolution to be able to make it so that I don't know, you have like some guarantee that whichever beliefs you kind of feed into this like mapping that tells you like what the default program would have been, but this is like close enough to the real one. And so maybe like there's some interesting like work to be done, and yeah, getting clarity on how continuous this function is, I guess. Like if you break things slightly, do the default programs like wildly change? Yeah, I don't know about that.
So like we know that the resolution of program equilibria, some of the methods at least, for example, the Gödelian numbering stuff, makes the resolution really brittle. As in, the brittleness is kind of leading to a catastrophic outcome. And such things, can we combine them with, say, fail-safes and SPI to say, oh, if, in our, program equilibrium resolution, it brittles, we fail, can we, renegotiate, whatever?
Yeah, I think that's a cool idea. I haven't thought of that, but I think it's like, it feels like less central than like agents having incompatible demands, and that's why it is incompatible, or why there's a miscoordination. But yeah, if like they're both aiming for the same equilibrium, but just the implementation is too brittle, yeah, maybe fail-safes can help with that too. You might still have like this like regressive, are the fail-safes also like brittle, but yeah, so particularly like how fail-safes would have to work, or like how SPI would work, and as like the big example of this is you need to be able to, reading this code to say like, are you committed to play this SPI as well? And if like the way that that's written is also really brittle, then it's also not going to work.
Yeah. But I mean, like in reality, I can kind of see this as like kind of levels of like social consensus, right? Maybe like everybody kind of agrees if nothing really bad happens, say like, oh, we both want to solve this program and then, it briefs, then we can kind of all agree that at least we need to solve to something that does not lead to us all defective. Then we have the same negotiation protocol, and that's like the same negotiation protocol is a focal on social consensus protocol that is easier to establish than like the specific program equilibrium commitment that we are trying to play in that specific game.
Yeah.
And so like, do you see?
Yeah. Tentatively, that sounds promising. Yeah, I think that's like a nice aspect of this discussion is like I'm like boxed in my theory land of here's this central motivating problem, but maybe missing other practical cases where this is important. Speaking of getting more concrete, I'm curious to dig into some of the stuff on here. I guess we talked about this issue of you get miscoordination from sort of a lag time between when it's a broadcast. So if anyone is like burning to share like some other example you've seen in the crypto space where this would be relevant, and need to hear that.
I mean, I kind of want to dig in more to the programming equilibrium resolution. Can we use SPIs to mitigate that problem? Yeah. So so over there, like if realistically we want to implement some kind of programming equilibria, if systems, let's say actually on blockchain, two users commit to some transaction, either a smart contract or some transactions that depend on other users' committed transactions, right? They simultaneously do the commitment, as their commitment are like interdependent. As like they want to play some specific game. Let's say I want to, settle some trade against you. Like I want to trade asset A to asset B. If you commit to trade asset B to asset A with me, and then then we set our trades. Then like we really don't want the brittleness to happen because maybe the brittleness is that we'll close some trade, but at least you want to like trade, just maybe we want to negotiate whatever, what the price, the terms. Yeah. So in that example, I would imagine maybe we have some like already established social consensus on that. Oh, if this first level program equilibrium resolution fails, then we all use this real time negotiation on blockchains to further negotiate the price. But then, like, to compute or to simulate those negotiation processes, it costs a lot of computation resources. Computation resources, as we know, is not that, but like it's kind of scarce blockchain. Do you see any way that we can like, further layer this process? Maybe like we compute the first level of program equilibrium resolution some like broad blockchain, and so like the negotiation process is taken care by a smaller set of nodes. And like, for example, it's just some designs around there. Welcome suggestion. Yeah. And for the blockchain people here, I mentioned it's because in a lot of the smart transactions talk, especially Vlad initially mentioned one of smart transactions usage is real-time user negotiation. And real-time user negotiation sounds a lot like, fail-safes and SPIs, where the commitment of the protocol is a negotiation protocol between users. I don't think Vlad has a specification or has thought about this deep, but I trust there are some interesting ideas to explore.
There you go. Well, you mentioned in one slide what Shane was talking about yesterday, where you have two incompatible commitments. But I didn't really understand how that ties into what they matter. And I feel like this has to do with this real-time negotiation problem, incompatible simultaneous commitments. Can you maybe just draw that link again?
Oh yeah. I guess I could literally draw it. And I don't want to get rid of this one. It's and don't want the pens down. There, where we go here. Yeah. So the argument is that if like at time t and this time t plus looks like a t as well. So like t is our block time. So in this region, there's no like broadcasting that can happen between those two times, as I understand it. So because there's no broadcasting, you might have like Bob submits a commitment here, Alice does here, and so Bob's might be to demand 70%. Alice's demand 50%. Kind of unconditionally. So basically, because there's no broadcasting, Alice doesn't see that Bob has like committed here, and so like makes any incompatible. Whereas like if there had been like a continuous time for broadcasting and Bob's commitment were broadcast, Alice could just say, "Oh, I'll go along with that," because the demand has been made. It's like, credible.
So the argument was that if I broadcast my commitment along with a pay-safe, in case the commitments don't resolve or the brittleness makes it that we don't find the efficient outcome. So if I make the demand, but also I have this pay-safe that's embedded in my commitment, I'm able to hedge against situations where I might get into outcomes where the commitments don't resolve. And then with the pay-safe, I can achieve the SPI outcome.
What would be a pay-safe in this scenario? Sorry, how would the pay-safe look like in this scenario?
Yeah, so there is this like layered question of which fail-safe is used exactly. Someone voice card and gets to me. So this is something that Casper's paper gets into, that like you kind of have a SPI selection problem in the sense of like, yeah, how do the agents agree on the failsafe? We'll suppose that there's, it's just suffice to say, in some scenarios, there is kind of like either like a unilateral SPI you can make, or it is bilateral, but sort of neither side can game it, and so they're all incentivized to at least go on with that failsafe, even if they don't get all the way further the frontier, because they still have to like solve SPI selection. The failsafe paper gives an example of this, but yeah, I think in general this like second order coordination problem crops up, but there are ways around it. So let's like say that that's been solved, then you could have like how would this work? In principle, so like if this is like on like here 100% goes to Alice, here 100% goes to Bob. This is quite messy. And the Pareto frontier is there. If what we stipulate happens when they don't trade is just like go down here, then the failsafe could just map this outcome to anything groups whatsoever. Like a kind of easy focal point to coordinate on would be like something that's fair in some sense. It could also, maybe I should just like illustrate the thing I was talking about, the example given in the paper, because this might just like make things more concrete.
Just do the sign situation like would something like I get the first, you get the first, and the first is burned.
And why do you burn it exactly?
Because we want by reality, perhaps 50% to like 50% failsafe would be equivalent of just saying we never do anything that valid the person, right? So we kind of want to have like most everything from the part of here using this person.
It's just a couple way of saying it on the frontier. But I think there's some thought for that again.
Sure. I think what I want to say is that the like burning might make sense if the reason you end up burning is they can't agree like getting all the way to the frontier, but like why do they agree and like at least that far is my question. And so this thing I'm gonna illustrate, if I can remember this properly, and give you a principled way of doing it. So let's say it's like Bob's demand when you're 0.7 to Bob and 0.3 to Alice, so it's up here. Alice's demand would like slip unfairly, so it's up here. And what they do is go to the intersection like these lines that are like perpendicular to these. Why is this nice? The reason is that like you can't game this by demanding more for yourself. If Bob like instead of having 0.7 went to like 0.9, and so this is this other demand made by Bob, but Alice is the same. Then the point goes down here, and Bob hasn't profited at all. So the nice property here is that like each player's allocation depends on the other player's demand, not on their own. But it's still a Pareto improvement on this one. I didn't come up with this, by the way. It's like, it's this blog post called Cooperating with Agents with Different Notions of Fairness Without Exploitability, something like that. Yeah, I really would have liked to cite an academic source on this in the paper, but it doesn't exist. So,
yeah, it's when you have videos like there's not like one that can be guys and
yeah.
We won't have the speaker. Oh wait, is that the?
Yeah.
Okay.
We do have this number as well. I probably yes. So come down to actually what's
Nothing but crypto beside Twitter threads.
Yeah. I could be decided on like in regular classes, like this talk, but in an academic paper, yeah. Yeah. I guess we're probably at time.
Yeah, we kind of okay. Okay.
You